So now let's walk through an example of caching. And in particular, we're going to look at caching instructions. So here's our setup. We've got a CPU and a small SRAM cache and our large DRAM memory. And we're going to walk through a program. So here's our program. It's got a loop in it. It's going to do add I and then branch. It'll jump either back to start or continue. If it doesn't jump back to start, it's going to do an add and then finally jump back to start again. So let's walk through this program. So on cycle 0, we want to do instruction 0. So we need to go get that instruction. So when we go get that instruction, the CPU is going to look in the cache, and it doesn't find it in the cache. It misses in the cache. So if it's not in the cache, we need to go to the DRAM. So the CPU is going to go to the DRAM, it's going to find that instruction, and load it into the cache. Now the DRAM is slow, so this is going to take 100 cycles. So what that means is that on cycle 100, we'll finally be ready to actually execute that instruction. So after we've executed our add I instruction, we need to go on to the next instruction, which is at address 4. So we're going to fetch address 4. The CPU looks in the cache, doesn't find address 4 in the cache, so it needs to go to DRAM. So it's going to go to DRAM, find address 4, load that into the cache, and remember the DRAM is slow, so this is going to take 100 cycles. So on cycle 201, we'll finally be ready to execute the BNE instruction. So then on cycle 202, we now jump back up to the add I instruction, can access the add I instruction. So we go and look, is the add I instruction in the cache? Yes, it is. So we had a hit. The instruction is in the cache, and we can go ahead and execute it in one cycle because it's in the cache. Now in cycle 203, we're going to do the BNE instruction again. So we look in the cache, it's in the cache, we had another cache hit, that's great, we can execute it in one cycle because it's in the cache. We go ahead and do that. But this time we don't branch back to start. Now we're going to go on to instruction 8. So we go and want to fetch instruction 8, we look in the cache, it's not in the cache, we have a miss. So if we miss in the cache, we then go to look in the DRAM. We find the instruction in the DRAM, we load it into the cache. Now the DRAM is slow, so this is going to take another 100 cycles. So on cycle 304, we now finally get to execute our add instruction. After cycle 304, we get to 305, and here we're going to go on to the last instruction, which is the jump. So we need to fetch this instruction. So again, the CPU looks in the cache, it's a miss, doesn't find it in the cache, so it's going to go to DRAM, take that instruction from DRAM, load it into the cache. This is going to take us 100 cycles. So in cycle 405, we finally got it in there, we can execute our jump instruction. Now we're going to go on to the next instruction, which is add I. So at this point, we're going to look in the cache, we find it in the cache, and in fact, all of the instructions are in the cache at this point. So now no matter which of these 4 instructions we do, we're always going to have a cache hit, which means the program's going to run really fast now because we've loaded it all into the cache. So here we found the add I instruction in the cache, do it in one cycle. We'll go on to the branch not equal instruction, find it in the cache, do it in one cycle. The add I instruction again is in the cache, the branch not equal is in the cache, the add is in the cache, the jump is in the cache, and the add I is in the cache. So we found all of these instructions in the cache, we're able to execute much faster. So once we got to that point in the program, everything was in the cache. So down here, we had one cycle per instruction because everything was in the cache. We got the ideal performance because we were running as if our memory was super fast. Up here, however, we hadn't yet loaded the instructions into the cache. So here our performance looked much more like we were using the slow DRAM because we had to load the data into the cache to get the good performance. So how many misses will the program in the example have in total? Well, it's going to have 4 misses in total. We have 4 instructions, and once we've gone through all 4 instructions and loaded them into the cache, we're never going to miss again. Well, we'd miss again if another program or something else pushed them out of the cache, but by itself, once this program has loaded all 4 instructions, it's never going to miss. How about if the program in the example was run on a processor with a 3-entry cache? How many misses would it have? Well, in this case, the number of misses is going to be proportional to the number of loop iterations. So every time the code moves from the top two, the add I and the BNE instructions, down to the bottom two, the add and the jump, it's going to have to kick out one of the instructions from the cache to load the new fourth instruction. And then when it goes back, it's going to have to do the same thing. So the more times the program goes through the loop, the more misses it's going to have.